Hey guys, sorry I couldn't be there today, but I'm hanging out at home with my two adorable redheads and just making sure that, they don't burn the house down. But what I wanted to go over with you is just a quick recap of what you should be working on today. We will be looking at a couple of things in these notes here in Target 2B, but you should also be working on the homework of Target 2A. All right, I did a couple of examples. I filled in the notes here for you so that you could have something to look back on. Don't worry too much about number 4. It's really not a big deal. If we had time in class, we're going to talk about the calculator and some of the problems with the graphing calculator and rational functions, because what you see there is all that you see on the screen. We don't see asymptotes, we don't see holes, and that makes it kind of hard to work with the calculator sometimes, which leads us into what we're talking about today: finding holes, finding asymptotes, and all that stuff algebraically and not relying on a graph. All right, so let's dig in here. And you can see in the notes, just a quick overview here. What we're going to do is we're just going to kind of go piece by piece and look at some different characteristics. Now, if you look at the last page here, notice we are not going to be asking you to find everything. There's only 8 characteristics here: domain, holes, x-intercepts, real zeros, y-intercepts, and then our 3 asymptotes. So at the end of the day, when we put everything together next week, this will be what we expect you to be able to find from a function algebraically, not looking at a graph. All right, so let's come back to the beginning here. And kind of, as I said above, there are times where our graphing utilities, our ability to graph, does not really give us enough accurate information to know everything we need to know about our rational functions. So what we're going to talk about first is how we find holes algebraically. Remember, a rational function is a fraction. There is a polynomial in the numerator and a polynomial in the denominator. Now, whenever you have a fraction, what that creates is the opportunity for something to cancel out. If you have the same factor in the numerator and denominator, they cancel each other, right? I'm just going to come over here. If I have something like, oops, let me get a pen going here. If I have something like 2x over 2y, well, 2 is a factor in the top, 2 is a factor in the bottom. They cancel, leaving me with just xy, right? Well, the same thing can happen in our rational functions, but instead of the factors just being a monomial or a constant, they're going to be possibly binomials as well. So let's take a look here. And finding the hole starts with looking if there is any factors in the numerator and denominator that will cancel. What that's going to do is that's going to give me the ability to find the x-coordinate of my hole. Once I have the x-coordinate of my hole, I can substitute that back into the function to find the y-coordinate and give me my ordered pair. So let's take a look at the first example here. So one thing you'll notice is this function is already written in the factored form in the numerator. Notice this is written as 3 binomial factors. All right, most times you're going to have to do the factoring yourself, but in this first example, we did it for you. Now, if you look, are there any factors in the numerator that are the same in the denominator? And hopefully you recognized that x minus 1 and x minus 1 are both factors in the numerator and denominator. So just as the 2's did on the example to the left, x minus 1 over x minus 1 will cancel out. Now, that does leave me with a simplified equation. And if you look at this, you might be saying to yourself, well, that's not even a rational function anymore, and it doesn't look like it. But here's the catch. We can't just ignore the fact that when we started this function, there was a variable in the denominator. And anytime that you have this situation where a variable in the denominator, a factor with a variable, cancels out, you are going to have a hole. All right? That's what creates algebraically a hole. So here's how we go about this. We're going to take what was canceled out of the denominator, and we're going to set it equal to 0, essentially trying to find the value that if you plugged it into the original equation would make the denominator 0 and cause the function to be undefined, right? So when we do that, we find x equals 1. So when in the original function, when x equaled 1, you would have nothing, right? If you plug 1 in the denominator, you would get 0, anything over 0, undefined. But a hole is an ordered pair. So how do I find the other half, the y-coordinate, when I know x is 1? Well, that's when we're going to use the simplified equation here to do that. So we're going to take the simplified f of x, and we're going to substitute 1 for x to find, we're going to substitute 1 for x here to find 5, right? So then f of 1 becomes 5 times 6, and f of 1 is 30. So if f of 1 is 30, that means my x-coordinate of my hole is 1, and the y-coordinate is 30. So that would be the ordered pair of the hole. We would have no domain value at 1 and no range value at 30 there. All right, let's take a look at a similar problem, but where we are not given the factored form. So if you look at this numerator, it is not factored. And we have x plus 3 in the denominator. Well, how do I know that there isn't a factor of x plus 3 hiding there? Well, we've got to factor the numerator. So I've got to be able to take x squared minus 7x minus 30 and write it, since it's a quadratic, as two binomials. Well, since my a value is 1, this problem is not too bad, right? A value is 1. Since a is 1, I can take negative 30 and negative 7 and find two numbers that multiply to negative 30 and add to negative 7, and those are the constants of my, my binomial factors. We should always remember that when a is 1, we can automatically know that the leading term in each binomial there is x, right? So what we got here, hopefully you have been thinking about that as I mentioned it, and you realize that it's negative 10 and 3. So my binomial factor here is negative 10 and plus 3. So what we can do is we can now replace x squared minus 7x minus 30 with its factored form. So what this really is x minus 10 times x plus 3 all over x plus 3. And hey, what do you know? There is a binomial factor that will cancel in both the numerator and denominator. All right, so what this means, here, let me just kind of section that off so we don't get confused. All right, this means when I simplify that, f of x just equals x minus 10. That's all I have left. But we've got to account for the hole that we would have because we canceled that x plus 3. So we set x plus 3 to 0 to figure out what value of x would cause the hole to exist, right? X equals negative 3, so that's the x value. So now I come into my simplified equation and plug in negative 3 for x so I can find the range, the y-coordinate, to finish my ordered pair, right? Negative 3 minus 10 is negative 13, and my hole would be negative 3, 13. So just to recap here, right? When we're looking for holes, what we're looking for are factors that will cancel in the numerator, between the numerator and denominator of our rational functions. The canceled denominator set equal to 0 gives me the x-coordinate of my hole, and then I substitute that value, that x value, into the simplified equation to find the y-coordinate. All right? Again, if you have any questions, if this was confusing, if this didn't make sense, please write them down, make a note, put a question mark and circle it or something like that on your paper, on your notes, and on Monday, we'll talk about it. All right. So we're going to probably try and talk about one more thing here before we call it a day. So now that we've talked about holes, we're going to talk about a few more characteristics here today in this video that can be found algebraically. All right, the first is the y-intercept. Now remember, guys, the y-intercept is an ordered pair where the x-coordinate is always 0 and the y-coordinate is some value, can be any number, but the x-coordinate has to be 0. So how do we find a y-intercept? Well, it's pretty straightforward. We substitute 0 in for x and we simplify to get y. So you plug 0 in for x, simplify, that's your y-coordinate, you got your y-intercept. All right, zeros. Zeros come when we solve for x, when the numerator is set equal to 0. Here's the deal. For any fraction to be equal to 0, the numerator must be equal to 0. It really doesn't matter what the denominator is, 0 over 100, 0 over 10, 0 over a million, 0 over -5. All of those simplify to 0 because the numerator is 0. So when we're looking for zeros, what we focus on is the numerator, all right? The x-intercept. Remember, the x-intercept is a real 0, but it is the x-coordinate of the x-intercept. All right, so what we're going to do is we're actually going to find zeros first and then use the zeros to write the x-intercepts. So graphically, we normally find the x-intercepts first and then do the zeros. Algebraically, we're finding zeros first and then doing x-intercepts. All right, vertical asymptotes are actually going to be pretty easy if we can find zeros, because we're going to do the same exact thing for vertical asymptotes that we did for zeros, but instead of the numerator being set equal to 0, it's going to be the denominator is equal to 0. This does come after, this is an important part, this comes after we already canceled out any wholes. All right, wholes are found first, then if there's anything left over in the denominator, then we find our vertical asymptotes. All right, so let's just do a couple examples here. I think you're going to find that these really aren't really not too bad here. Okay, so find the intercepts, the zeros, and the vertical asymptotes from f of x. Again, notice this one is already fully factored for you, so that's kind of nice to start with. All right, let's go first with our y-intercept. So to find the y-intercept, guys, all we're going to do is I'm just going to plug in 0 wherever there is an x value here. So this is going to become 0 minus 4 times 0 minus 1 times 0 plus 5 all over 0 plus 2 and 0 minus 3. Okay, so simplify that. This is -4 times -1, which is +4, times 5, which is 20. And this is 2 times -3, which is -6. All right, and if you take your calculator and you divide 20 by 6, you are going to get -3.3 repeating. So the y-intercept is the ordered pair 0, 3.3 -3.33. All right, pretty straightforward, pretty easy. I apologize, I didn't realize I wrote so big because I zoomed in. I'm going to make this a little smaller to make sure I have room for everything here. Okay, so that is my y-intercept. So let's move on to x-intercept, right? X-intercept, we set the numerator equal to 0. So to find, well, I'm sorry, I got ahead of myself here. We're not finding the x-intercept, we're finding the zeros, and then we're going to use the zeros to get the x-intercept. So they kind of go hand in hand, but we're really finding zeros. So what we're going to do is we're just going to take the numerator here, x minus 4 times x minus 1 times x plus 5, and set it equal to 0. Now, since this is already written in the factored form, this is really easy. We just use the zero product property. If I have factors set equal to 0, I can set each factor on its own equal to 0 to find the solutions of the equation, right? This is just what we learned back in the day with the zero product property. So I'm going to find x equals 4, x equals 1, and x equals -5. So my zeros are 4, 1, and -5. All right, x-intercepts, pretty straightforward. 4, 0, 1, 0, -5, 0. All right, one more thing to look at here is the vertical asymptotes. Now, we're going to do the same exact thing we just did to find our zeros, but we're going to do it with the denominator. If the numerator is 0, the entire fraction is 0. If the denominator is 0, the entire fraction is undefined. And that's what our vertical asymptotes tell us from the graph. So I'm going to have x plus 2 times x minus 3 equals 0. Again, we're going to use zero product property, right? Turn these factors into equations, and what I'm going to get here are two equations, x equals -2 and x equals 3. And those would be the equations of my vertical asymptotes there. All right, so we're going to stop here. We'll do this second example together on Monday, but I think I've given you enough information here. Again, I'm not expecting you to understand everything we just did. What I want is for you to think about it, examine it, reflect on it, what makes sense, what doesn't make sense, and let's ask questions about what doesn't make sense. Hope you guys have a great extended weekend, and I realized I said I would see you on Monday. That is not true, because we are not in school on Monday. I'll see you on Tuesday. Have a good one, guys.